Hi, I'm Captain Sunil Bhaba from Marine Gurukul. In this video, we explore the gyro compass error, specifically the course latitude and speed error, which is also known as the steaming error of the gyro compass. Gyro compass is a very critical equipment for ship's navigation, and it is important to be aware of the errors which can creep in the gyro readings. Moreover, we also get questions in our competency exams based on the theory as well as numerical related to this topic. This explanation will certainly help you to answer all these types of questions. So with this understanding, let us now discuss about the cause of the steaming error, the formula for calculation of the steaming error, and also the derivation of the steaming error using a very simple method. The course latitude and speed error is also known as CLSE. In short, C for the course, L for the latitude, S for speed, and E for error. And it is also known as the steaming error. The name steaming error is given as it is generated only when the ship is steaming. Now a gyro compass basically is a free gyroscope which is controlled and damped to make it north seeking and then remain pointing towards north. Now at the first instance, it may appear that a free gyro which is controlled and damped is sensing and then pointing towards the northerly direction directly. But if we go a little deep into the concept of the gyro compass, actually the gyro compass is sensing the direction in which it is being taken due to the rotation of the earth. The rotation of the earth is in the easterly direction. So I will repeat once again. The gyro compass is sensing the direction in which it is being taken due to the rotation of the earth, which is the easterly direction, and then aligning its spin axis perpendicular to this direction, that is the easterly direction, which results in the spin axis pointing towards north. Now a doubt may arise, how does the gyro sense the direction of rotation of the earth? This can be easily understood if we look at the property of gyroscopic inertia. Gyroscopic inertia explains that a free gyro follows the motion of a gyrostar. Now the basis of the motion of a gyrostar and all other celestial bodies is the rotation of the earth itself. Star in itself is a fixed body, practically fixed body on the celestial sphere. The reason why the stars appear to move to us in their declination circles is because of the rotation of the earth. Hence, the basic principle of the gyro senses the direction of the rotation of the earth and aligns its spin axis perpendicular to this direction. Now the gyroscope pointing towards north is actually aligned in a direction perpendicular to the direction of the rotation of the earth, which is easterly. The gyroscope pointing in a direction perpendicular to the direction of rotation of the earth works very well as long as the gyro is kept stationary. But if the gyro is placed on a moving vessel, the gyro then senses the resultant of the Earth's easterly motion and the vessel's own motion and aligns itself perpendicular to this resultant. Let's now try to understand this concept using a diagram. A diagram makes it very easy to understand the concept as well as the CLSE, course latitude speed error. Also, the diagram helps us to derive the formula for calculation of the CLSE or the steaming error. Let's first assume that our ship is at this particular location. You can see this point A coming up on the screen. Now the Earth is taking the ship in the easterly direction, and this motion of the ship because of the rotation of the Earth is represented by this red color vector. The magnitude of this vector is given by 900 cos latitude. The Earth is moving in the easterly direction. For an observer who is on the equator, latitude becoming 0, this comes to 900 miles per hour or 900 knots. And for a person which is on the pole, the latitude becoming 90 degrees, the cos of 90 factor becomes 0. So this motion, rotation of the Earth, this particular motion at the pole becomes 0. Between the equator and the pole, the direction will be easterly, and the magnitude with which the Earth is taking us in the easterly direction will be somewhere between 900 and 0. Let's mark the end of this vector as delta D. So alpha delta represents the Earth's motion vector. Now let's assume that our ship is moving on a northeasterly course. Now let's show the motion of the ship, the motion vector of the ship. You can see this blue color vector coming up in the diagram. The vector alpha bravo represents the course and speed of the ship. It represents the motion of the ship. The vessel is moving in a northeasterly direction, and this vector is represented by the alphabet V, Victor. Now since the Earth is taking us in the easterly direction, perpendicular to this particular direction, we have the true north. So you can see the true north also coming up in the diagram. True north is perpendicular to the easterly direction in which the Earth is taking us. Also, you can clearly see now that this blue color angle which we have, the angle between the true north and the ship's course and speed vector, that is alpha bravo, this blue color angle represents the course of the ship. Now let's try to find the resultant of these two motions which the ship is undertaking. The ship is being taken in the easterly direction by the rotation of the Earth, and because of its engine, the ship is moving in the direction of AB, the course which is being steered. Now let's find out the resultant of these two vectors, these two motions. Now for finding the resultant, we use the parallelogram method of vector addition. So we make a parallelogram. We make this vector bravo to Charlie, which is exactly same as vector alpha to delta. So alpha delta and bravo Charlie are exactly in the same direction and having the same magnitude. Likewise, we draw a vector parallel to vector alpha bravo representing the course and speed of the ship, and you can see a blue color vector delta to Charlie coming up in the diagram, which is exactly same in direction as well as magnitude to the course and speed or course and distance vector of the ship. So we have the parallelogram of both these motions. And if we draw the diagonal of this parallelogram, you see the diagonal coming up. Alpha Charlie is the diagonal of this parallelogram. That gives us the resultant motion of the Earth's motion as well as the ship's motion. So if we view the motion of the ship from space, the vessel will be moving in the direction of the resultant, that is vector alpha to Charlie. So this is the direction in which the ship is being taken because of the rotation of the Earth as well as because of its own motion due to its own engines. Now we are aware that the gyro senses this direction in which it is being taken, and the gyro spin axis aligns itself perpendicular to this particular direction. So as per that principle, the gyro spin axis should be perpendicular to the resultant vector, that is the alpha Charlie vector. So let us show the gyro spin axis direction now. You can see this green color arrow coming up in the diagram, which is perpendicular to the resultant vector alpha Charlie, and this represents the direction in which the spin axis of the gyro points. And The direction in which the spin axis points is known as the gyro north. So you can now see in this particular diagram, we have the true north represented by the red arrow perpendicular to the direction of rotation of the earth, and we also have the gyro north represented by the green color arrow perpendicular to the resultant in which the ship is being taken because of the earth's rotation as well as its own motion. Now the difference between these two vectors, that is the difference between the gyro north and the true north, is the CLSE, course latitude speed error, or the steaming error. The gyro is pointing in the direction of the green color vector, the true north is in the direction of the red color vector, and the difference between them represented by this green color angle is the CLSE, or the steaming error. Now we have seen that the difference between the gyro north and the true north, this green color angle which is being formed, is the CLSE. Now this CLSE, or this green color angle, is exactly same as the angle DAC, delta alpha Charlie. Let me mark this angle in the diagram. You can see this particular angle now coming up in the diagram. This is angle delta alpha Charlie. This particular angle is exactly same as the CLSE angle which we had shown earlier. Now why these two angles are same is because of a geometry principle which says that the angle between two lines is the same as the angle between their perpendiculars. The initial CLSE which we observed was between the true north and the gyro north. We are aware that the Earth's easterly motion, which is red color vector alpha delta, is perpendicular to true north, and we are aware that the resultant vector green color vector alpha Charlie is perpendicular to gyro north. So the angle between gyro north and true north will be exactly the same as angle between vector alpha to delta and vector alpha to Charlie. So that explains that the angle delta alpha Charlie, represented as green color angle here and marked as CLSE, is our steaming error. Also, another thing which we can note is if you take your attention to angle delta alpha Bravo. The angle delta alpha Bravo, which is the red color angle now shown in the diagram, this angle is equal to 90 minus course of the ship. We have marked this angle as angle theta here. So this angle theta is equal to 90 minus course. We can easily understand it from the diagram. The red vector here represents the true north. Now from the true north to the easterly direction represented by alpha delta, the total angle is 90 degrees. This total angle is 90 degrees. And the blue color angle which we have is the course of the ship. So the remaining angle, that is delta alpha Bravo, is theta angle and equal to 90 minus course. Now moving further in our diagram, we now extend the alpha delta vector further. So you can see this dotted line coming up in the diagram, and we have extended the alpha delta vector further in the easterly direction. Also, now let us drop a perpendicular to this alpha delta extended from point C, point Charlie. So let's drop a perpendicular. You can now see a perpendicular being dropped from point Charlie to the alpha delta vector extended. This perpendicular meets the horizontal line, the alpha delta vector, at point P, and we are aware that this angle will be 90 degrees. Angle P is going to be 90 degrees. Now also, if you look carefully, the angle Papa Delta Charlie, will be exactly equal to the angle theta which we had in our diagram here, the red color angle. So angle Papa Delta Charlie is equal to angle Delta Alpha Bravo. That's because Alpha Bravo and Delta Charlie are parallel to each other, both representing the course and distance vector of the ship. So that's why angle Papa Delta Charlie is equal to theta. Now if you pay your attention to this right angle triangle, that is Papa Delta Charlie, considering angle theta in this right angle triangle Papa Delta Charlie, you will be able to appreciate that side Delta Charlie is the hypotenuse, side Delta to Papa is the base in this triangle considering angle theta, and side Papa to Charlie or Charlie to Papa is the perpendicular. Now using the trigonometric ratios of cos theta and sin theta, we can easily find out the sides Papa to Delta or Delta Papa and Charlie Papa. So if we use these ratios, we can easily find out that Delta Papa side is given by V cos theta. V is the magnitude of the ship's course and distance vector. So this vector multiplied by cos theta gives us the side Delta to Papa. And the side Charlie to Papa is given by V sin theta. So this is a simple application of the trigonometric ratios of cos theta and sin theta. And this is also a simple application of the vector resolution. We have basically resolved this vector Delta Charlie or vector into two components, V cos theta and V sin theta. This will help us in derivation of the CLSE formula. Having understood the diagram, now we can easily derive the formula for calculation of the CLSE or steaming error. Now for this, let's take our attention to the triangle Papa Alpha Charlie. So we have a right angle triangle in this diagram, Papa Alpha Charlie, having a right angle at point Papa at point P. So in this right angle triangle, we have this angle A as our CLSE. Now let's take the tangent of this CLSE, tangent of this particular angle. Now tangent of CLSE will be equal to perpendicular upon base. The perpendicular in this case is going to be side Charlie to Papa, which is V sin theta. And the base is going to be alpha to Papa, which is 900 cos lat plus V cos theta. So the same thing is mentioned here. You can see tangent of CLSE is equal to V sin theta, which is the perpendicular, divided by 900 cos lat plus V cos theta, which is the base. So tangent theta equal to perpendicular upon base. Now we are aware in this diagram that this angle theta, the red color angle, is basically 90 minus course of the ship. So let's replace this angle theta in our equation by 90 minus course. Once we replace this angle theta by 90 minus course, the equation turns out to be tangent of CLSE is equal to V sin 90 minus course. Instead of theta, we are having 90 minus course here, divided by 900 cos lat plus V cos 90 minus course. Instead of V cos theta, we have V cos 90 minus course now. Now we are aware that sine of 90 minus an angle is equal to cos of that angle. And thus the formula now converts to tangent of CLSE is equal to V cos course. Sine of 90 minus course becomes cos course. So the numerator turns out to be V cos course divided by 900 cos lat plus V sin course. Cos of 90 minus course in the previous steps, cos of 90 minus course converts to sine of course. Thus bringing us to the formula. Tangent of CLSE is equal to V cos course divided by 900 cos lat plus V sin course. So this is the formula for course latitude and speed error, also known as steaming error, when the vessel is moving in the northeasterly quadrant. Also, you can see that the error which is generated in this particular case is westerly error. The gyro error is west, or the CLSE is west, because the gyro north is towards the west of the true north. Now, if the ship goes in other quadrants, if the ship is steering a course in some other quadrant, let us say for example southeasterly quadrant or southwesterly quadrant or northwesterly quadrant, there is going to be a slight change in the formula. And for each and every quadrant, the formula can be derived using the same principle. We can make exactly a similar diagram showing the course of the ship in whichever quadrant it is, and using the same method, the formula can be derived in all the quadrants. Let me now take you to the final formula which can be used in any of the quadrants. The formula which we have is tangent of CLSE is equal to V cos course divided by 900 cos lat plus minus V sin course. CLSE is the course latitude speed error or the steaming error. V is the speed of the ship. Course is the quadrantal course on which the ship is moving. 900 cos latitude, it is the latitude where the ship is, plus minus V sin course. V again is the speed of the ship and course is the quadrantal course on which the ship is moving. Now in the denominator we have a plus and minus sign here. When do we use a plus and when do we use a minus? The positive sign or plus sign is used for easterly courses, and the negative sign is used whenever the vessel is moving on westerly courses. So if the ship is moving on a northeasterly course or a southeasterly course, we will be using a plus here in the denominator. And if the vessel is moving on a northwesterly course or a southwesterly course having a westerly component, we will be using a negative sign here. You can easily understand the concept behind it. When the ship is moving in the easterly direction, it is adding up to the easterly motion of the ship. The easterly motion of the earth. And whenever the vessel is moving in a westerly direction, it is reducing the easterly motion of the earth. Now, once we put all these values here in the formula, we are going to get the magnitude of the CLSE or the steaming error. Now, how do we determine whether this error is east or west, whether this error is low or high? Now, for that, error is high or west on northerly courses and the error is low or east on southerly courses. If the vessel's course is having a northerly component, that means vessel is moving on a northeasterly course or a northwesterly course, the error is going to be west or high. West and high are interchangeable. You can easily confirm it from the idiom which we use for applying the compass error. Error west, compass west. So a westerly error is also mentioned as high error. Whenever the vessel is moving on a southerly component course, that is a southeasterly course or a southwesterly course, the error is going to be east or low. Again, east and low are interchangeable. We can confirm it from the idiom error east, compass least. So in case of a southerly component course, the error is going to be easterly or low. Now be careful when you are applying this formula. The easterly or westerly component of the course decides whether we will be having a plus or minus sign here in the denominator, whereas The north and south component of the course decides the sign of the error, whether the error is going to be high or low. This brings us to the end of this video. If this video has helped you, please do like and share our content. This motivates us to generate more content similar to this one. Also, this helps these kind of videos reach out to more people. In case you need any kind of further support, please write to us on marinegurukul@gmail.com. Thank you very much for watching this video. I wish you all the best.